If you trace the path of a single particle kicked around by unseen collisions, its trajectory looks like an unpredictable mess. Yet, when 10,000 of these paths unfold together, their distance from the origin expands at a rate proportional to the square root of time. How does microscopic randomness forge such a precise macroscopic law? By the end, you will see exactly why this chaotic wandering has no choice but to obey it. To see where our standard intuition fails, let us zoom in on a single yellow path and try to measure its speed. In ordinary motion, tracking an object over a tiny time interval gives a well-behaved ratio of distance to time. But watch what happens as we zoom in on this wandering particle. The closer we look, the more jagged turns reveal themselves. The total path length along those zigzags grows longer and longer, while the net straight line displacement stays stubbornly small. If you try to calculate standard velocity here, the answer completely explodes. Let us test this with a concrete comparison. Imagine a green marble rolling smoothly along a straight line at 1 unit per second. In 1 second, it travels 1 unit. In 4 seconds, it reaches 4 units. Distance grows directly with time. Now consider our yellow wandering particle. In 1 second, it ends up about 1 unit from where it started. But after 4 seconds, it does not reach 4 units. On average, it is only 2 units away. Quadrupling the elapsed time only doubles the net displacement. This reveals the vivid tension at the heart of Brownian motion. At the microscopic scale, the particle is kicked violently in every direction, moving along a wildly infinite path. Yet at the macroscopic scale, its outward progress slows down dramatically, governed by the square root of time. Classical calculus, built on smooth curves and well-defined velocities, fails to capture this chaotic wandering. To unlock this mystery, we must change our perspective. In the next chapter, we will discover the hidden quantity that ticks like a perfect clock. To understand why distance grows as the square root of time, let us simplify the picture. Imagine our yellow particle constrained to move along a single straight line, taking equal steps of length 1, either to the right or to the left, with equal probability. If you ask for the average final position after many steps, the answer is unhelpful. Positive steps and negative steps cancel out, leaving an average position of 0. But what if, instead of average position, we track the average squared distance from the origin? Squaring turns every negative step into a positive number, preventing those cancellations. Let us work through a simple case with exactly 2 steps. There are 4 equally likely paths the particle can take. It can step right twice to end at positive 2, step left twice to end at negative 2, or step right then left, or left then right, both ending right back at 0. Now let us square each final displacement. 2 squared is 4. Negative 2 squared is also 4. 0 squared is 0. If we average these 4 outcomes, 4, 0, 0, and 4, we get exactly 2. After 2 steps, the average squared distance is precisely 2. This is not a coincidence. For any number of steps, the total displacement is the sum of each individual step. When we square that total sum, basic algebra splits the result into 2 kinds of terms: squared individual steps and cross-product pairs of different steps. Because each step is either +1 or -1, every squared step is always +1. But what about the cross products? Because each future step is completely independent of the past, positive and negative cross terms cancel out perfectly on average. Only the squared steps survive. Since every squared step contributes exactly 1 to the total, taking n steps gives an average square displacement of n. And because physical time is simply proportional to the total number of microscopic steps, average squared displacement grows linearly with time. To recover actual distance, we take the square root of both sides. This is why distance grows with the square root of time. Squared distance acts as a steady, reliable clock ticking quietly beneath the chaos. In the next chapter, we will see how this discrete clock lets us count steps across a continuous spatial grid. Instead of tracking just one particle, let us widen our view to an entire cloud of them scattered along a one-dimensional grid. Imagine measuring the density of particles at position x at time t. To find out how many particles arrive at position x in the very next time step, we do not need to guess where each individual path goes. We only need to look at the immediate neighbors. Every particle ending up at x right now must have taken its final step either from the left, at x minus delta x, or from the right, at x plus delta x. Since our particle steps left or right with equal probability, exactly half of the particles at position x minus delta x will step right onto position x. Likewise, half of the particles at x plus delta x will step left onto x. This gives us a fundamental balance equation. The probability density at position x at time t plus delta t equals 1/2 times the density at x minus delta x plus 1/2 times the density at x plus delta x times. This simple average of neighbors determines the entire future state. To connect these discrete jumps to continuous space, we need a mathematical bridge. And that bridge is the Taylor series. If delta x is very small, we can approximate the probability at the neighboring points using derivatives at position x. The value at x plus delta x is roughly the value at x plus delta x times the spatial derivative, plus 1/2 delta x squared times the second derivative. When we do the same expansion for x minus delta x, notice what happens to that first derivative term. Its sign flips. When we average those two neighboring expansions together, something remarkable occurs. The odd terms, the first derivatives, cancel out completely because stepping left and stepping right are equally likely. The spatial bias disappears. What remains on the right-hand side is simply the original value plus 1/2 delta x squared times the second spatial derivative. Meanwhile, expanding the left-hand side in time gives the current density plus delta t times the time derivative. Microscopic randomness is just transformed into a relationship between derivatives. Up to this point, we assumed our particle takes neat equal steps of length 1 to the left or right. But real fluid collisions are far dirtier. A particle might get struck hard to the right, nudged gently to the left, or barely moved at all. You might worry that changing these microscopic rules would alter the macroscopic picture entirely. Remarkably, it does not. Whether steps are symmetric coin flips or wild, irregular leaps, the macroscopic distribution of a large collection of particles always converges to the exact same smooth shape. To see why this happens, watch what occurs as we sum together successive independent steps. With just one step, the probability distribution inherits all the jagged asymmetry of our microscopic rule. But when a particle takes 2 steps, the distribution broadens and softens as different combinations combine. By 5 steps, those sharp spikes are almost completely erased. By 30 steps, any trace of the original microscopic rule has vanished into a single perfectly smooth bell curve. This universal smoothing is the Central Limit Theorem in action. When you sum many independent random variables, the fine details of their individual distributions get washed away. Only 2 microscopic quantities survive at the macroscopic scale: the mean position, which sets the center, and the step variance, which sets the rate of spreading. Because each step acts independently, the total variance simply grows proportionally with the number of steps, and therefore directly with elapsed time. This forces any random walk, no matter how chaotic at the microscopic scale, to converge to a precise Gaussian probability distribution. The width of this bell curve expands at a rate governed by the square root of time, tying our square root clock directly to the shape of uncertainty itself. But this brings us to a profound perspective shift. If the density of particles always forms a smooth bell curve, can we drop the randomness entirely and describe its evolution with a deterministic differential equation? In the next chapter, we will see how chaos resolves into the heat equation. Let us revisit the Taylor expansion we built earlier. On the left side, we had delta t times the rate of change of probability over time. On the right side, after all the odd terms canceled out, we were left with 1/2 delta x squared times the second spatial derivative. If we divide both sides by delta t, a remarkable ratio appears in front of that spatial derivative, delta x squared divided by 2 delta t. To keep our physical world stable as microscopic steps grow infinitely small, this ratio must settle into a constant number which we call the diffusion coefficient, d. This gives us one of the most celebrated equations in all of mathematical physics, the heat equation. The partial derivative of probability density with respect to time equals the diffusion coefficient times the second spatial derivative. Notice what this equation is actually telling us. The rate at which density rises or falls at any point depends entirely on spatial curvature. Where the bell curve is concave down-peaked, at the center density leaks away into the surroundings. Where it is concave up in the flat outer tails, density flows in and fills the void. And here is the magic of this perspective shift. At the level of a single particle, the future is pure uncertainty, a sequence of unpredictable kicks. But when we track the entire distribution, every trace of randomness vanishes. The evolution of the probability curve is completely deterministic. If you know the density profile right now, the heat equation tells you its exact shape at any future moment. Randomness at the microscopic scale has transmuted into smooth, predictable flow at the macroscopic scale, behaving precisely like heat diffusing along a metal rod. Now remember the Gaussian dull curve we found in the last chapter? If you plug that exact Gaussian formula into the heat equation, both sides balance perfectly. The expanding bell curve is not just an empirical approximation, it is the fundamental solution to the heat equation starting from a single point. But this raises a deep mathematical question. If the continuous density profile evolves so smoothly, why does an individual particle path remain violently jagged no matter how far we zoom in? In the final chapter, we will see why classical calculus breaks down for individual paths, forcing us to discover stochastic calculus. If you try to apply classical calculus to an individual Brownian path, you immediately run into a bizarre contradiction. In standard calculus, when you zoom in on a smooth curve over a tiny time interval, delta t, the change in position, delta x, is proportional to delta t. If you square that change, delta x squared, it scales with delta t squared, a term so vanishingly small that calculus throws it away. But remember our square root clock. For Brownian motion, delta x scales with the square root of delta t. That means delta x squared is proportional to delta t itself, not delta t squared. This non-vanishing square has a profound consequence when we apply functions to a random path. Suppose we want to track a quantity like position squared or any smooth function f of our Brownian path b. In classical calculus, the Taylor series expansion lets us drop the second derivative term, because delta x squared vanishes much faster than delta t. But for Brownian motion, because delta b squared is directly proportional to delta t, that second derivative term refuses to disappear. It survives into the final derivative, contributing a systematic deterministic drift to the change in f. This famous adjustment is the core of Ito's lemma, the fundamental theorem of stochastic calculus. The microscopic path remains endlessly jagged and nowhere differentiable, defying standard derivatives. Yet, its quadratic variation is as smooth and steady as time itself. This is the deep secret of Brownian motion. The very fractal roughness that destroys standard calculus is what creates the extra deterministic term, perfectly bridging microscopic randomness with macroscopic order. By looking past smooth curves, we discover a richer geometry where chaos and calculus exist in perfect harmony. You can now look at an impossibly tangled path and see a predictable square root law quietly governing its spread. This delicate balance between random noise and smooth drift shapes everything from stock prices to quantum fluctuations. If a particle diffuses in 2 dimensions instead of 1, how far from the origin will it drift on average?